So we have a block of glass here. We're going to have a light ray coming into the surface, and that light ray is going to bend towards the normal. This is going to be our normal here. Remember, the normal is perpendicular to the surface. There's at right angles to the surface, and I guess there's an assumption we have to make that this is air, and the refractive index for air is 1.0. So that's going to be important for our calculations later. But we've got a light ray coming in that's going to bend towards the normal. So let's just make sure we've got the same thickness of line. It's going to bend towards the normal, and then at this surface, let's redraw our normal on there. Different normal for a different surface. As it's leaving, it's going to bend away from the normal. So it's going, and in fact it will be parallel to this initial ray. So we've got three sections, one here on its when it's incident inside the block, two inside the block, three when it's leaving the block. And we're going to perform calculations between 1 and 2 and between 2 and 3 just to work out what angles we're going to find. And the formula that we're going to use for this is Snell's Law. We'll just write that up the top here. Remember, that is N1 sine theta 1 equals N2 sine theta 2. My 2 is a little bit cramped up there. Okay, running out of space, shrink that, put it all up there, and see if we can do the workings surrounding it. So we've got, for the first situation, going from 1 to 2. We actually need an angle, so I'm going to state that this first initial angle is 20 degrees. Okay, so what we need to do is find out the angle inside the glass block. That's going to be theta 2. My N1 is going to be air of 1.0. Let's write this into the equation as we go. 1.0, so it's N1 times by sine of that initial angle, 20 degrees. That's going to equal N2, which is 1.5, times by sine of this other angle, theta 2, on the inside. We don't know what it is, we're going to have to calculate that. So we're trying to find theta 2. Let's rearrange. We can rearrange before we input all of the values. This is a relatively simple equation, so it doesn't really matter which order we do these in. For complex things, it's better to do all the rearrangements first and substitute right at the end. But anyway, we're going to divide both sides by 1.5 because that will cancel out this part, and then we're going to have to do one more slightly tricky thing. Let's move that up a little bit. Because we've got on the right hand side now sine theta 2 equals everything on the left hand side, we're going to have to take the inverse sine function to cancel out the sine function. So I'm going to write this out in full so it's very clear. 1.0, let's scratch that, inverse sine function, sine to the negative 1, and that's just second function or shift on your calculator. 1.0 sine of 20 divided by 1.5, and that will be sine to the negative 1 times sine of theta, which gives us theta 2 by itself. So I've got a calculator here prepared today, so I'm going to plug that in and see what we come up with. I'm just going to say how I'm typing this into my calculator, and that might help you as well. So I'm going to go sine of 20 degrees, find the answer to that, which is about 0.34, and then I'm going to multiply that by 1.0 over, there's a fraction, over 1.5. and I'm expecting, because 1.0 over 1.5 is approximately, well, it is 2/3, so I'll expect about 2/3 of my answer, which is what I get, so 0.228. Now I need to take the inverse sign of that, so I'm going to go second function, or shift, sine, and then the previous answer, and that gives me 13.1 degrees, actually 13.2. But now I'm going to write this out in full because this is not our final step. Theta 2 equals 13.18. Everything's given to me in two significant figures, but I'm writing this to four significant figures just to give me enough unrounded numbers and digits to use for the final. So 13.18 degrees, that's really important. That's going to be the same angle as, where are we? There we go. This angle here. So that angle is the same as that angle which we just calculated. That was theta 2. This is also theta 2. And it has to be just because you have let's see if we can just draw a quick little diagram to show you. You have two parallel lines, which are your two normals, and you've got a line going between them. So this angle here has to be the same as that angle because of your rules of geometry. I don't know the exact name of it. Could be co-interior angles. But anyway, those angles there are the same. So now, for our next calculation, pick a different colour so it's a bit easier to see what's going on. N1 is 1.5 because we're going from inside the block to outside. So let's just write that from 2 to 3. N1 is 1.5 times by sine of theta 1, which in this case is the 13.18 degrees. 13.18 degrees. That's going to equal N2, which in this case is 1.0 back in air, times by sine of theta 2, which we don't know. And if you're really sharp, you will have noticed that this is the exact reverse of the equation that we had down here. So on the left hand side we've got 1.5 sine 13.8. If I go and have a look at my equation here, we found theta 2 was 13.18, and that means on the original right hand side we would have had here 1.5 sine of 13.8. That means I can know the answer is 1.0 sine 20 degrees, and I can know that we should have 20 degrees coming out for this. But let's just go through just to double check and make sure. Skipping straight to the final stage, because the working is the same. This is inverse sine function of 1.5 sine 13.18 degrees over 1.0 equals theta 2, which is the right hand side furthest most one. And I'm going to plug this into the calculator using my unrounded value. So sine of 13.8 times by 1.5 over 1.0. Over 1.0 is additional and unneeded, because when you divide by 1 you're not really changing anything. And then second function, sine of that answer gives me 20 degrees. 19.999 recurring, so we've lost a tiny fraction through the calculation, but when I round it, that gives me a clear 20 degrees, which is really nice. So that's Snell's law in action. There is one more special case of Snell's law, and that is dealing with total internal reflection, which is a subject for another time. Thank you.